let's look at some of the things necessary for things to go into orbit. What do we need? The trick, you have to make your satellite move sideways really fast. The Earth moves at almost 30,000 meters per second in its orbit around the Sun. If it wasn't going this fast, the Sun's gravity would pull the Earth into the inner solar system. The Sun is not pulling the Earth around in its orbit. The Sun is merely changing the direction it travels. The Earth formed from material that was swirling around the newly formed Sun, and at our distance from the Sun, the material that was going at the right speed stayed at that distance and clumped together because of mutual gravitational attraction. But at this distance, anything going too slow would fall toward the inner solar system. Anything going faster would move farther out. We need no propulsion once we're orbiting at the right speed at the right place. This shows a primitive way to put things in orbit. Suppose you could be at the yellow dot at the top center of the picture, maybe standing on a tower. If you just drop an object, it will fall straight down, following the path labeled A in the diagram. If you launch the object horizontally to the right, if it's not going very fast, it might follow the path labeled B. So it would come down this path right here. If you launch the object faster and faster, it could follow the paths labeled C through F. Path C is still going to strike the surface of the Earth. Path D is the first orbit that we see here. Although it's not a circular orbit, it would get closer to the surface of the Earth here. On this scale, it would still be above nearly all of the Earth's atmosphere, and so it could complete an orbit there. Path E is the one that's just right. It would be a circular orbit, always staying the same distance away from the surface of the Earth. Path F is going at the point up here where it starts. It's going a little faster than it needs to for an orbit, and as a result, its farthest point in the orbit is quite a ways above the surface of the Earth, and it would continue on, but when it gets here, it's not going fast enough to stay there, and so it would then come in and reach that same point. That would be an elliptical orbit. And elliptical orbits are just fine. Usually when we put things in low Earth orbit, they are actually about as low as this one is down here at the bottom all the way around. That's a typical orbit for like the International Space Station or the Hubble Space Telescope. They're not that far above the Earth's surface. Also required, get it above the atmosphere. This is key. An object moving through the Earth's atmosphere at a speed fast enough to orbit, which is almost 5 miles per second, is going to get very hot from friction with the air it's moving through. The leading edges of the wings and fuselage of the space shuttles were covered with ceramic material several inches thick to prevent that heat from working its way into the interior of the fuselage or into the support structure of the wings. When the Space Shuttle Columbia was launched in January 2003, a piece of foam insulation broke off one of the external tanks right here. See that circled there, and it struck the leading edge of the left wing right down here. It wasn't noticed at the time. External cameras on the shuttle, though, captured the separation of the insulation from the tank and the impact with the shuttle about 2 seconds later. The estimated speed of the piece was somewhere between 400 and 600 miles an hour relative to the shuttle when it struck the wing. Shortly after launch, people at NASA realized that the insulation had fallen off and might have struck the shuttle. They had all sorts of meetings and communications back and forth in the next few days without telling the people on the orbiting shuttle about this. And they decided that they would go ahead with the mission and return to Earth. When the mission was ended and the shuttle was returning to land in Florida, parts of the shuttle began coming off while still over California. A lot of people would watch shuttle re-entries and follow it with telescopes and things like that. So there were people on the ground in California just space lovers, more or less, and they saw pieces coming off even while it was over California. It was going fast enough that it was only about 6 minutes before it was over Texas, and somewhere over Texas it just blew completely apart. None of the crew survived. The heat of re-entry had more or less melted the wing off the shuttle, and it lost all of its flight ability at that point. One of the crewmen on the shuttle is named Michael P. Anderson, and he went to Cheney High School, graduated from there. Highway 904, which if you go to Cheney, you'll take that. It goes from Interstate 90 to Cheney, and it's called the Michael P. Anderson Memorial Highway. Just as an example of something orbiting in low Earth orbit, the Hubble Space Telescope, I think I've mentioned what its altitude is a few times in here. It's about 350 miles above the surface of the Earth. I should be giving these in kilometers, but I haven't converted all of those. It travels more than 17,000 miles per hour, and it has an orbital period of about 90 minutes. 17,000 miles per hour is pretty fast. There's a website called Heavens Above, and you can go there and search for passes of things like International Space Station. Here's some for February 2022. None of these passes are visible. They happen to be during daytime. Right now, that's what's going on. When I clicked passes to include, I selected all of the passes, and so you can see them going over here. But something you can see from this, it flies over appearing first at 9:47 in the morning, and it has its high point at about 9:50 in the morning. And then about an hour and a half later, it's actually a little more than an hour and a half, it has another flyover, 11:27, which is actually about 97 minutes later. The Earth is turning under the path of the satellite, and so that can alter the time between when it's visible. So you can see things like that going on. Here are some from later in February and going into early March that are actually visible. Here I selected only the visible ones. That means they'll be happening during darkness. And let's see, 5 o'clock in the morning is when this first one first becomes visible, 10 degrees above the southern horizon. Its highest point is only 16 degrees above the southeastern horizon, and then it sets 10 degrees above the eastern horizon. This is a pretty quick flyover, although it's 4 minutes and 44 seconds, so that would be long enough to be noticeable. Magnitude minus 1.1. It's brighter than every star in the sky except Sirius, so you might be able to see that. There's some other ones down here which are really spectacular. This one on the 24th of February, magnitude minus 3.8. If you're in a dark spot, that is bright enough to cast a shadow. Now, this is also around 5 o'clock in the morning, but this one's much higher. Starts off 61 degrees above the southwestern horizon. That's when the International Space Station will go from being in the shadow of the Earth to being out of the shadow of the Earth, and it's sunlight reflecting off of the International Space Station that lets you see it. It doesn't have its own light system that's lighting it up that bright. It's just reflected sunlight. You can track these things down at Heavens Above. They're kind of fun to look at. So we've got the Hubble Space Telescope completing orbits in 90 minutes. There's another Earth satellite, the Moon. It's just another satellite, but it's only going 2,300 miles an hour, and it has an orbital period of 27.3 days. These are both following the same rules. The Hubble Space Telescope and Earth's moon, they're acted on by Earth's gravitation. That's what sets the rule for an orbit. Doesn't matter if it's natural or artificial. In between 27.3 days and 90 minutes, you can pick about any orbital period you want. The Hubble Space Telescope is roughly the minimum for a low Earth orbit satellite, or the International Space Station might be. You can have orbital periods that match the Earth's rotation rate. A geostationary satellite is one that is parked above the equator of the Earth and has an orbital period of 23 hours and 56 minutes. It stays parked above the same point on the equator as the Earth turns. And from any point on the Earth for where that satellite is visible, it'll stay fixed in the same point in space. And so if you have Dish Network or DirecTV, your TV antenna outside your house is aimed at one of these satellites, a geostationary satellite. They were actually predicted by a science fiction writer, or a person who's known for his science fiction writing, named Arthur C. Clarke. He wrote a book called 2001 that a famous sci-fi movie was made of. But Clarke predicted these orbits, and sometimes these geostationary orbits are called Clarke orbits as a result. In another video, I'll look at applying Newton's law of gravitation to orbital motion, and we'll see how you can get an expression for the orbital speed from that, as well as some other things that you can learn. And in another video, we'll learn about tides. So this is as far, but now you have a good idea what it takes to get something into orbit.